you for coming. So come in, join us. Who among you have ever written a Python program and thought, this is too slow. I wish it could be faster. Like 3 times faster would just be enough to be satisfying. Or is your snake-based program too lethargic and just laying in the sun, not doing really what you want it to do? Do you wish you could just poke it and make it go faster, as if after a mouse or so? Well, I have a solution for you. Your program won't run 3 times as fast or 4 times as fast. No, 10, 100 times faster. And this is what I'm selling. Now, unlike the salesmen of snake oil entrepreneurs of yesteryear, this fella is more of the organic kind of rich in omega-3, seems to have some health benefits similar to cod oil or salmon. Picture is by the Department of Agriculture, Fishery and Conservation from Hong Kong. Thanks to them for letting me use it. Now, who am I? Sindre Nistad, similar pronunciation to Cinder. Work at Beauvais, which is a consultant, been working there for 8 years or so now, doing front-end, back-end, cloud, DevOps stuff. Some of that involves running native code on Python. So, who have seen this one before? Some. So this is an illustration of the first, when this structure was first discovered in 1978 or thereabouts by Mr. Mandelbrot at IBM, and used a fairly chunky mainframe and a really old printer which didn't quite work, which is why this is so clean. And they spent quite a bit of time to create this, so let's do the same. There will be live coding here. So let's just run it, see what happens. Which, not great, not terrible. I mean, it works, it generates a picture. Not too sharp, but we can fix that. And so, performance-wise, not great. Though it may be useful. Maybe you just wanted to create one picture and not actually move around. But for our purposes, we want to move around, we want to interact with it. So what can we do? Well, you need to know why it's slow. There are a couple of tools for that, like the built-in C profile, which will measure every line of execution, how long it takes. There's also PySpy, Scalene, Austin, Perf. If you're doing NVIDIA stuff, they also have a profiler. We're mostly just going to use the first one, the built-in and PySpy. So let's first measure what takes time here. Now, profiling generally adds a bit of overhead. So as you may notice that the frame counter here is higher, which means slower in this case, because it's not frames per second. This is seconds per frame, which we want it the other way around. So this has probably run for long enough, and we have gathered some measurements. And obviously the interaction also takes a while, so we get some nice statistics. We can see that one function is called like 6 million times, another one a bit more, and there are some for loops. So how does this function look like? So it's essentially this function, which is executed a few million times per image, which takes a while. Further, it's a for loop, so we iterate over the whole image. That takes a bit of time, and then we apply some color to it. Now, the code itself is fairly straightforward. There's an initialization, some state for where we are in the image, how we move around, and a frame counter, which we will be using to measure performance gains. And then some computation, updating the screen and updating the frame counter. So we could try NumPy, ufunc, universal functions, which is a way of turning any function into a function that's executed per element on a matrix, which is more efficient. So we have one of them. Which will look fairly similar to the pure implementation we just showed. So a little bit of decorator, some differences, and here, instead of a double for loop, we just define that we want the index of a certain shape, and these return as matrices. So this is a matrix, or multiple numbers. This is the same. So let's see how this works. We're just executing it as a module, and somewhat better, not great, but we're on the right track. From before, we saw that the function Mandelbrot took a lot of time to execute, so let's just write that in C instead. Now, this is regular Python, and so we can do some cool stuff. So this used to be a decorator, but that's just a function that calls a function, so let's call another function, which we need to import first. We'll have a look at how the function looks shortly, but let's see it in action first. Oops. Oh, come on. Just executing it. Yeah. Instead of, notice that the terms have reversed. Now we're running frames per second and not seconds per frame, which is progress. So we can actually move around and zoom. We can explore this as we see fit. Still not great, but progress. So why don't we just write the whole, let's see the function first. So essentially the same as before. We just have a little bit of decorator, like removing the GIL and making sure it can be called from Python. Nothing too fancy. So why don't we just write the entire thing in C instead? Which is quite useful. Now, if you want to profile Cython, you can add these comments, but we're not going to because they can be very, very slow. So, going back to our main function. So, this one is very similar to the pure Python, and lower number. That's not good. Why? Well, one good thing about the Cython is that it will generate C code for us, so we can, and it will also annotate the code. So my apologies for the lack of syntax highlighting. This is what you get from Cython. The important part is bright yellow means interaction with Python, and there is a lot of it, which we don't want because we want performance. So let's just do the whole thing in C. Now we're getting somewhere. So this one is a bit different from before. So the main function is still the same, but instead we are first removing the GIL and we're running it in parallel, which is generally a good tip for performance, especially in this case because the function is independent of everything else, so we can just do it multiple times. And we're not really allocating anything anymore, so yeah, it's pretty good. Now, how can we improve this performance? We can by profiling it with this time's PySpy. And we need to do this in Linux because we're doing a native profiling with subsystem. Doesn't quite work in Windows, so we're just doing it in you don't see it here because sometimes Windows subsystem for Linux crashes, but let's just do it again. What is live demo without some hiccups? So now we're just activating a environment, and in this case I'm using UV because it's quite convenient. And we want it to be just showing what's going on. So we use stop. We could export it to some kind of graph or so, but we don't care about that now. You may have noticed that the main method is called underscore underscore main underscore underscore, which allows us to call it as a module. Right. We also need to tell UV to actually use the sourced environment. Otherwise, it will try to overwrite the existing Windows virtual environment, which is not great. It will take a while to build otherwise. So notice that the frame rate is down to seconds per frame again. The reason for that is that we're actually profiling what's going on in the C extension as well. And we see some curious things here, like sine, cosine. Did you see any sine or cosine in the code so far? Me neither. And there's also some increment memory view, which, well, we can figure that out. Again, Cython will give you C code, so we can just inspect it. Which is a lot. Like a lot. So one of the main culprit was something sine, something cosine, so let's search for that. Oh, one hit, yay. Makes life so much easier. And where is this called? In that seems about reasonable. Where is this called? Here. That's the offending line. Now, we just want the number to be multiplied by itself, and we don't have any optimization on, so let's just do that. Oops. Type. So this is the one, right? So let's change this to multiply by itself. And because we don't want to recompile this and then find out another thing, we notice that another function is this one, which, let's find it. So where is it used? Here. Right, because we're slicing something and that is a Python thing, so let's just do it in C because we know what the size is. So this is the color channel, which is 3 because RGB. Oops. And let's not execute the profiler just to see how would the performance have changed, if anything. Since we changed the Cython code, it actually needs to recompile, understandably enough. That's done. Yay. Now this is actually usable, kind of. But if we're not too concerned with the darker parts, which require more iterations, then good. So mission accomplished? Nah. One thing to note in this code is that bounds check and seed division, YOLO, because who needs to check if you're inside the memory? What can possibly go wrong? So what if you want something memory safe, like say Rust? So similar. Quite similar as before, just with more oxidation. So let's do that. And we change the implementation. Now this is still on Ubuntu, but we could have executed that. So good. Not as good as the optimized Cython, but that's probably because I'm not that familiar with Rust, and yeah. But still, quite a lot better, even with my naive implementation, than pure Python. But what if you don't care about compilers and don't want to write a C extension and whatnot? Well, there are other things, like Numba, which if we have a look at it, is quite similar to the pure version I showed first. So this is the difference where the Numba version is on the left and the pure version is on the right. So we're just importing something, adding a decorator with some typing, and still bounce check, who needs them? Similar here. The only difference here is we're doing it in parallel as before. So let's see. Notice it takes a little bit more time to start up because I lied, there is compilation in here. It's just in time. So it's quite good. With quite literally just adding a few decorator and installing a few packages. So for computational heavy task, this might be it. But one thing to note here is that so the processor is active, it's using it. But I notice we also have this fella, which is not being used much. Nice thing is, we can. Python has some really nice things. So the Rust part was done with Maturin and PyO3, which has been talked about here multiple times. I won't go deeper than it works, if you're familiar with Rust and prepared to do some troubleshooting. And we just looked at Numba, so links are here. There will be a QR code at the end, which you can use to read on more information. But in particular, this machine has a GPU, NVIDIA, as it happens, and they recently came out with drivers, or with a Python package, where you can write CUDA kernels for Python and interact with the drivers directly in Python through CUDA core. There is also PyOpenCL, which is similar for OpenCL, which should be usable on other cards than NVIDIA. Now, let's see here. This should be NVIDIA, right? And we need, there we go. So the setup, let's not look too closely at that because it's a lot. So here is a actual CUDA kernel, actual C++, fairly similar to what we have before, only it took a while to get the GPU to actually work. So there was some blue screens every now and then, to the point where one screen had a blue screen, the other screen didn't. So hopefully that won't happen here. Now, previously we've had one simple class that is as an interface to the compute, which usually just do the compute, do the coloring, return. This time, a bit more. We set up the driver and compiler for the CUDA kernel, compile the code, do the code. So this one is fairly straightforward. And then we pass in all of the things, and we keep a reference to what we actually want out. But this is a lot of code and not a lot of pretty colors. So let's change that. There we go. Oops. Let's see. Takes a little while to compile here as well, because usually you can't really get away with compilation. But, oops, there's the mouse. Not bad. Now, it has to be said that GPUs are really good at the 32-bit float, but we need the double precision of 64-bit float, which they are less good at, because otherwise you can zoom in at about this level and then pixels. In this case, though, this seems interesting. There's many pretty things here, which you can explore freely. So, oh, now here's the problem. Now, this is, each pixel is the width of a floating point number. Floating points, as may have been said before here, is lying to you. It's not the real. They have certain distances between them, and here you see them. But still, and that's some of the good things with Python. And there are other tools as well, as you can use free-threaded Python, which has been mentioned a lot. Couldn't get it to work because I need to recompile Pygame with free-threaded Python on Windows, which didn't work, unfortunately. There's also writing your own C extension and using PyBind, NumPy, and HPy. There's LPython, which is an LLVM, not LLM, because that would be quite different. Implementation, you can also write the Fortran if you're so inclined. And there are other implementations like PyPy, Graal, Codon, ASPy, and so forth. And that's all.
Thank you for the amazing session. So it's time for questions. We have 5 minutes for questions.
So I hope this can be some inspiration of things to do and how you can improve performance, though remember, always measure that you're actually getting an improvement performance and know what you want and know what is good enough. So source code, presentation, all of that on here, you can run it, execute it, if you so choose.
Do we have any questions? Okay. So I can't see any. So feel free to post on Discord channel if you have questions. Thanks again.